Hey guys, in this video we're going to talk about Chapter 2, Section 3, Linear Equations. So I want to give you some intuition for why, we're doing what we're doing. And so I think the best way to do that is to give you a couple of real-world examples to illustrate, linear equations and how we can solve them and what that means in a real-world context. So let's consider the situation. You're going to be in town for just a couple of months because of work, and you want to join a gym. And so there's two gyms in town. One gym is Jerry's gym, and the other gym is called Frank's Fitness Gym. So Jerry's gym charges new members a one-time fee of $10 and then $15 per month. And maybe I should have done that in yellow. Let's do that in yellow. Okay, and then Frank's gym charges new members a one-time fee of $40 and then $5 per month. So both scenarios, both Jerry's gym, the cost of Jerry's gym, and the cost of Frank's gym are both linear situations. And so the first thing we want to do is write some linear equations to represent these situations. So remember, with linear equations, we can write them in the form y equals mx plus b, where b is the y-intercept, also known as the initial value, and m is the slope, or the rate of change. So let's look at Jerry's gym. So Jerry's gym is charging a one-time registration fee, which means that the initial value is $10, because if you stay for 0 months, you're going to have to pay $10, and that's all you'll have to pay. So that is my starting value, and that's going to tell me that $10 is going to be B in this case. And the second thing we need is the slope. So remember, the slope is how much we're changing per unit of time, right? So because it tells us that we're going up by $15 per month per unit of time, that's going to be our slope here. So m is 15. And so we can write a function that represents the situation, the cost of Jerry's gym. We can say that the cost, c of x, which you can think of as y, it's just the output. We can say the cost is going to be equal to m, which is 15, times x plus b. So you could use c of x for cost. You could also use y. Maybe we'll just use y to stay consistent. But the point is that y represents the cost. And what does x represent? X is our independent variable, what we are in control of changing. Well, what we're in control of changing is how many months we stay at the gym, right? And, from previous lectures, we know that x is 90% of the time it's going to represent time. So this is going to be our months. So that's our equation for Jerry's gym. Now let's go ahead and write an equation for Frank's gym. So Frank charges new members a one-time fee of $40. So this time our y-intercept, aka our initial value, is going to be $40. That's how much we're paying just by walking in the door at 0 months. And then we're going to pay $5 per month. So that means my rate of change is 5. M is 5. And so my equation is going to be y equals mx plus b. And that is our equation here. And again, y is going to represent the cost, and x is going to represent the month. So we just did this right in linear equations to represent the situations. Okay. So now that we have our equations, we can use Desmos to analyze the lines, the graphs that represent the equations. So the blue graph, 10 plus 15x, that's going to represent Jerry's gym. So I'll just write Jerry here, and maybe I'll even write equals y, just to stay consistent with the previous slide. And then this green one is going to represent Frank's gem. So let's go ahead and talk about the implications of the graph. So we can look at, we can look at these things in two ways. We can talk about, what the situation means graphically and what it means algebraically, and I want to discuss both of them. So it says, when is Jerry's gem the better deal for you? Now, Jerry's gem is the blue line. And algebraically, what that means is when is the cost less for Jerry's gem, right? When is it the better deal? So the way that we can set this up, the cost of Jerry's gem, we just said, was 10 plus 15x. That's the cost, right? It equals y. Y is the cost. So what we want to say is, when is the cost of Jerry's gem, 10 plus 15x, less than the cost of Frank's gem, which is 40 plus 5x, right? And I'm going to do this off to the side just to show you guys the math here. So we have 10 plus 15x. When is that less than 40 plus 5x? So when is the cost of Jerry's gem less than the cost of Frank's gem? And what we can do is we can solve this just like an equation. We can, group the x's on one side and group the constants on one side. So the first thing I can do to start off by solving this is I can subtract 5x from both sides of the less than sign. And what I get on the left side is 10. 15x minus 5x is 10x is less than 40. All right. So I am going to go ahead and at this point subtract 10 on both sides to get that 10x on the left is less than 30 on the right. And finally, I'll divide both sides by 10 to get x alone, and I get x is less than 3. So that's my answer here. Now, what did x represent? Well, we saw here that x represent the months and y, or the actual function, represents the cost. So what this means is the months, when the months are less than 3. Or maybe we should say it like this. Maybe we should say less than 3 months. Less than 3 months. And let's write it up here. That's our answer. So if I'm staying at the gym for less than 3 months, then I should go with Jerry's gym instead of Frank's. Now, when is Frank's gym the better deal for you? Well, this is a very similar situation. The only thing we're going to do is we're going to set up the inequality. So that means, basically an equation, but with a less than or greater than sign. We're going to set it up a little bit differently. Because this time, what we want to know is when is Frank's gym the better deal? So Frank's gym, the cost of that is represented by 40 plus 5x. So our equation is, well, when is 40 plus 5x less than Jerry's gym, 10 plus 15x? When is the cost of Frank's gym less than the cost of Jerry's gym? And again, we can solve this just like we did with the previous problem. I can subtract 5x from both sides, and I get 40 on the left is less than 10 plus 10x on the right. I'll subtract 10 from both sides to get on the left 30 is less than 10x. And finally, I can divide both sides by 10 to give me x is greater than 3. Now, whenever I read these inequalities, I always start with the variable. I said x is greater than 3 because the sign is opening up towards the variable. Whereas before, what we had was x is less than 3. We read it left to right, and it's less than because the point is facing the variable. So x is greater than 3. We can also write it like this so it's not backwards. As long as it's opening up towards the x, we're in good shape. And so what does this mean in our particular situation? It means more than 3 months, right? So if we're staying at this gym more than 3 months, we should go with Frank's gym. It's going to be cheaper for us if we're staying more than 3 months. So let's write that here. Now let's take a look at what these two questions look like graphically. So keep in mind that the green line is Frank's gym and the blue line is Jerry's gym. So with the first question, when is Jerry's gym the better deal for you? Less than 3 months. Well, that's going to be in between, let's see, that's going to be this right here, this section. So we can see, and actually maybe I'll do this. This is what I circled represents when X is less than 3 months. So, here X is 0, here X is, 1, all the way until X is 3. So that circled portion represents all values when X is less than 3. And what we can see is that Jerry's line is always under Frank's line, right? It's always cheaper. So that's how we can see it graphically. Whereas if we take a look at what happens with number 2, more than 3 months is going to be represented by this portion up here. So that's more than 3 months, and we can always see that Frank's line is below Jerry's line, and it's always cheaper. So that's how we can see that graphically. Now, you might be guessing for the next question, we might not have to do this algebraically, we can just look at it. After how many months will the cost be the same? Well, the cost is the same when these two lines cross. When they have the exact same height, the cost is the same. And we can prove this to ourselves algebraically, so we can see that the cost is $55 at 3 months, right? We can prove this to ourselves algebraically by setting the cost of Jerry's gym, 10 plus 15x, equal to the cost of Frank's gym, 40 plus 5x, and solving. So let's go ahead and do this. I'm going to subtract 5x from both sides. And on the left, I get 10 plus 10x. On the right, I'm just left with 40. I'll go ahead and subtract 10 on both sides. And I get 10x on the left equals 30 on the right. Dividing both sides by 10, I get exactly what I thought, x equals 3. So this means at 3 months, so our answer here is 3 months. At 3 months, both gyms will cost, well, what they're going to cost is the output, or the y value, 55. Now, how do we see that algebraically without looking at the graph? Well, we can go back to either one of our original functions. So we could go back to Jerry's function or Frank's function and plug in 3 for x. It doesn't matter which one you pick, you're going to get the same answer. But if I pick Jerry's function, I'm going to get 10 plus 15 times 3. I'm just plugging in 3 for x. This is a function. So at 3 months, how much is it going to cost? Well, if we do the addition and multiplication, we get 10 plus 45, which is indeed 55. So that's how you can see it algebraically. You could have used this function and plugged in 3 for x and got the same answer. So that is how we do those kinds of problems. Let's do another example, this time with an internet plan. So a company offers customers 2 plans for the internet. Plan A is $30 for the modem and $5 per month. Pretty cheap if you ask me. It's a pretty good deal. Plan B, the modem's free, but you pay $10 a month. Both really good deals. This problem must have been written in the 80s or something, or whenever the internet came out, the 90s, early 90s. So we want to represent these two plans in terms of linear equations because they're linear, right? After every month, we're going up by a set amount of money. So let's look at plan A first. So we need two things for a linear function. We need b, which is the y-intercept, and we need slope, which is the amount we're changing per month. Now the y-intercept can also be thought of as the initial value, the starting amount when time equals 0. So if you don't get internet for, if you get internet for 0 months, before the clock starts, how much are you paying? Well, you're paying $30 for plan A because you have to buy the modem. That's the fixed cost. So if you have a fixed cost, that's going to be our lowercase b, our y-intercept. And $5 per month, that's going to be my slope because remember, slope is the rate of change per unit of time. In this case, our unit of time is months. So we're increasing by $5 every single month. So our equation for plan A is y equals m, which is 5, x plus b. So that's our equation for plan A. Now let's go ahead and look at plan B. So plan B, the modem's free. So what is that telling us about our fixed cost? Our y-intercept is going to be 0, right? We don't have to pay anything for our fixed cost. However, it's going to be $10 a month. So the amount that I'm changing per month is 10. That's my slope. So y is equal to m, which is 10x plus b. Now, I don't like writing plus 0 because it's kind of just, you're writing more than you need to. So I'm just going to write y equals 10x to represent plan B. All right, so I have plan A and plan B plotted here. So this is plan A. And maybe I'll just put the y equals. So this is plan A. And I did all of this on the Desmos graphing calculator. And, if you just Google Desmos graphing calculator, this will come up and you can use it for your homework. So first one is plan A, which is green. Second one is going to be plan B, which is the purple line. And I want to answer some of these questions and analyze these problems algebraically as well as graphically. Now we have the graph from Desmos, pretty clear here. So let's first look at the first question algebraically. So it says after blank months, the plans cost the same. Well, the cost, so again, the cost, how much I'm paying is going to be our y, our output of the function. In other words, so since y is 10x, the cost is 10x. Since y is 30 plus 5x, the cost is 30 plus 5x. So that's going to be the cost, and my x is going to be how many months I choose to get internet for, my unit of time. So what I can do here is I can just say, well, when are the plans going to cost the same? Well, I can just set the respective cost equal to each other. I can say, well, I'm going to set the cost of plan A, which is 30 plus 5x, equal to the cost of plan B, which is 10x. And I'm going to go ahead and solve for x here. So to do that, I can group the x's on one side by first subtracting 5x on both sides. And I get 30 on the left side equals 5x on the right side. And then I can divide both sides by 5 to get x alone. So when I divide both sides by 5, I get x equals 6. So that is how I do this algebraically. So this is going to be after 6 months. That's my answer here. We can see this on the graph by seeing where the lines intersect. So where is the cost the same? That occurs when the height is the same. That occurs when the y value is the same. All of these things mean the exact same thing. So we can see that after 6 months, the plans cost, what, $60, right? Because that's our y value. So after 6 months, they both cost $60. And let's look at this algebraically. We just did that graphically, but let's look at this algebraically. So remember what we can do So we have two cost functions. The first cost function is 30 plus 5x. So if I plug in an x value, if I plug in a number of months, I get out a cost. And then my other one is 10x. Now, since these are going to be, I'm going to get the same thing because of this intersection point right here. So either function I can use. So if I use this function, I'm going to get y equals 10. I know that my x was 6, so I can simply plug in 6 to get $60 here, and that's how I do that algebraically. I could have also done it right here. I could have said, well, if I plug in 6 for x, I get y equals 30 plus 5 times 6. 30 plus 30 is 60, and I would have gotten the same answer either way. So that's how we do that algebraically. Okay, so the next question says you will need internet for 9 months. How much money will you save by going with plan A as opposed to plan B? So keep in mind that this is the cost for plan A, and the cost for plan B is 10x. So we want to see what happens at 9 months for both of these. How much is it going to cost for plan A versus plan B? So what we're going to do is, this is a function. We can plug in 9 for 9 months into x and get out an answer for y. So when we plug in 9 for x, we get 30 plus 5 times 9. 45 plus 30 is 75. So this is telling me that it's going to cost me $75 for the internet with plan A for 9 months. Now for plan B, I'm going to do the same thing. I'm plugging in 9 in for my input value to see what I get for my output. So if I do 10 times 9, I'm going to get $90. So it's obviously more expensive to go with plan B versus plan A if we're getting internet for 9 months, but how much more expensive? Well, we want to see what the difference is. So the difference is going to be 90 minus 75, which is equal to 15. So this is my answer here. I'm saving $15 by going with plan A versus plan B. All right. So I'm actually, weirdly enough, making this video when people are looking for the submarine that went down to look at the Titanic. Hopefully those people are okay. I don't really know what the outcome is at this moment, but kind of weird that I picked a submarine problem. Anyway, 2 submarines are currently underwater, and they begin to ascend, aka rise, right? Rise to the surface at a constant rate. Sub A is currently 900 feet below the surface of the water, and it's ascending at a rate of 150 feet per minute. Meanwhile, sub B is 400 feet below the surface and is ascending at a rate of 50 feet per minute. And so both of these situations are linear because we're rising at a set amount per unit of time. The set amount per unit of time in sub A is going to be 150, right? Because I'm rising 150 per unit of time, which in this case is minutes. Now, what is my y-intercept? What is my initial value? Well, if the surface is at 0, like if you imagine the surface of the water is at 0, and we go 900 feet below, this is going to be negative 900, not 900. If we were 900 feet above the surface, it'd be, positive 900. But since we're below, I'm going to say that our y-intercept is negative 900. So for sub A, our equation is y equals m, which is 150, x plus a negative 900, which is just negative 900. All right. So that's our equation for sub A. For sub B, our constant rate of change is 50. We're rising 50 feet per minute. So that's going to be our m. and our y-intercept is minus 400 because that's the starting value. We start at minus 400 feet below the surface. So my equation for sub B is going to be y equals 50x minus 400. So those are my two linear equations. So let's take a look at this graphically and answer some questions. So in green, it looks like we have sub A. So I'll just do, this is sub A in green. And in black, we have sub B. Okay. So after how many minutes are the submarines at the same height? Again, there's two different ways to approach this. Remember that we need to figure out what our variables are. So again, x is always time if we have a time variable. I shouldn't say always, but most of the time it is. So in this case, remember our time was minutes, right? Our slope was in feet per minute. Slope is change in y over change in x. So the y value is going to be feet, and the x value is going to be minutes, right? So slope is change in y over change in x. So y over x, we got feet. Maybe I'll erase this. So for y, we got feet, and for x, we have minutes, feet per minute. Okay, so we know y is feet, and then x is minutes. So feet's going to be the height, and so this is basically saying, hey, how many minutes are the submarines going to be at the same height? And we can see when that occurs on the graph, right? That's at that intersection point. They have the same height of negative 150 at 5 minutes, right? So that's how we see that graphically, and then we can answer the second question. Both submarines are at negative 150 feet at 5 minutes. Because remember, this first value is x, the second one is y. I can also look at this algebraically. So remember, y is the height, or in feet, and so what we can do is we can set the height in feet of sub A, which is 150 minus 900, that's y, okay? Y equals that, it's the same thing as that, equals the height of sub B, 50x minus 400, and I can solve for x this way. So I can first subtract 50x from both sides, and I get 100x minus 900 is going to equal minus 400. From here, I can add 900 to both sides, and I get 100 times x on the left equals 500 on the right. Finally, I can divide both sides by 100 to get x alone. X is going to be equal to 5. So that's how we can see that algebraically. And to actually figure out the height algebraically, I can take either of these equations. I'm going to just take the first one, which was 150x minus 900, and plug in 5 to see what I get. Again, I could have used the second equation, 50x minus 400, but it doesn't matter. So when you evaluate this out, you should indeed get negative 150. So that's how we can do that purely algebraically. Graphically, all we have to do is look at the intersection point. Okay, so let's go ahead and answer these next questions, and I'm just going to use the graph to do this. We could set up inequalities, but just for the purpose of time and, we already did some problems like that with the inequalities, I'm just going to look at the graph. So first question, it's when is sub A below sub B? So remember, sub A is the green line, and we can see that the green line is below the black line, when x is less than 5, right? Because, let's see. So like right here, x is 4, x is 3, x is 2, x is 1, and anything in between. Those all correspond to those x values, right? We can see those x values there. So our answer here is when x is less than 5. So This means less than 5 minutes because that's what our x is. All right, and then when is sub b below sub a? So sub b is the black line. We can see that sub b is below sub a when x is actually bigger than 5. Greater than 5 minutes, so like at 10 minutes, the black line is below the green line. At 15 minutes, the black line is below the green line. So any time where our minutes are greater than 5, sub b is below sub a. Okay, so we can also have, trying to find solutions kind of abstractly, like we're not given any particular situation, which in my opinion is easier. But I wanted to give you guys the real world context for like why we're even doing this, why it matters, why it's cool. But let's look at some problems where we're not given a specific situation. For number 1, we're given 2 lines. We're given the first line is y equals 2x minus 5, and the second line is y equals 6x plus 1. We want to find the solution algebraically and graphically. So graphically is the easiest thing to do because you can literally just put this in Desmos. So graphically, we have 2x minus 5 and 6x plus 1. Okay, 2x minus 5. Okay, so we can see graphically that these lines are going to cross at x equals negative 1.5. So let's prove this algebraically. So remember what we do. We're trying to find when the heights are the same. So we basically set the y values equal to each other. So the first y value is 2x minus 5, right? Y equals that. And the second y value is 6x plus 1. And we can go ahead and solve this for x by just solving this equation like we usually do. So I can go ahead and subtract 2x on both sides. And when I do that on the left, I'm left with negative 5. On the right, when I do 6x minus 2x, I'm left with 4x, and then that plus 1. So from here, I can subtract 1 on both sides of the equation to give me negative 6 on the left equals 4x on the right. And finally, I can divide both sides by 4 to give me x is equal to negative 1.5 when I do 6 divided by 4 in the calculator. So that's how we can do that algebraically, and we looked at it graphically by just plugging these in and looking at Desmos. So notice that with this problem, we had 2 y equals mx plus b equations set equal to each other, right? On the left side, m was 2, b was negative 5, and on the right side, m was 6 and b is 1. So we're not given y's here, but we can see that on the right side, m is 7 and b is 0. So that's our first line, is just 7x plus 0, or simply 7x. What's our second line? So our second line, we need to simplify first before because it's not in y equals mx plus b form quite yet. But I can distribute that 3 in there. So 3 times x is 3x, and 3 times negative 1 is negative 3. So, and again, we have 7x on the right side. So this is in y equals mx plus b form. M is equal to 3, and b is equal to negative 3. Mx plus b. So now I can put it in Desmos and it'll give me a line. Alright, now all we're going to do is tap on their intersection and we can see that they intersect at x equals negative 0.75. So that's what we should get when we set these equal to each other. So let's continue the algebra. What I can do at this point, so I'm looking at this line right here, line number 2. What I can do is I can subtract 3x from both sides to get the x's on one side. And when I do that, what I'm left with on the left side is negative 3, and on the right side I'm left with 4x. Finally, if I divide both sides by 4, I get x alone, and I get x is equal to negative 3/4, which indeed equals negative 0.75. So that is my answer there, and we confirm that graphically as well. Okay, so let's look at number 3. Now I'm going to separate the left side from the right side, and I can see that the left side is indeed in y equals mx plus b form. I have m is 2, that's the number attached to x, and I have b is positive 1. On the left side, it looks a little weird because it's a fraction, but it is secretly disguised in mx plus b form. We just have to write it a little bit differently. Since negative 5x plus 1 is all over 3, I can separate the terms out by writing this fraction as negative 5/3 x plus 1/3. And hopefully you guys can see that this is the same thing as this. I'm just using the laws of fraction addition to separate the fractions out. So now I'm in mx plus b form. So I have the line 2x plus 1 on the right side, and I have the line negative 5/3 x plus 1/3 on the left side. So these are two lines equaling each other, and I want to see where they intersect on Desmos. Was it plus 1 or minus 1? Let's see. Okay. All right, so let me zoom in just a little bit here. I'm going to press their intersection. So it looks like they intersect at x equals negative 0.182. So let's confirm that with our algebra. Okay, so I'm going to just get rid of this to make it a little bit cleaner. So what I can do to the left side, I don't like fractions, I don't. So what I can do to get rid of the fractions on the left, since both fractions have a 3 in the bottom, I can multiply both sides by 3/1. That's going to clear the fraction, okay? So when I distribute this thing, I get 3/1 times negative 5/3x, and these 3's cancel out, right? I'm just left with negative 5x. So when I distribute that first one, I'm left with negative 5x, and the whole point was to get rid of the fraction. When I distribute the 3/1 times the positive 1/3, well, again, the 3's cancel and I'm just left with 1. So I'm just left with a positive 1 here. So on the left, when I do that, I get negative 5x plus 3. When I do 3 times 1, I get 3. When I do 3 times 2x, I get 6x, right? Right, the 1 is kind of irrelevant, so 3/1 times 2x is 6x, plus 1 times 3/1 is 3, all right? So that's my new equation. Now I can group my x's, and I'm going to start that process by adding 5x to both sides. And when I do that on the left side, I'm left with 1, and on the right side, I'm left with 11x plus 3. Now I can subtract 3 from both sides. And I'm left with negative 2 equals 11x. Finally, I'll divide both sides by 11 to give me x equals negative 2/11, and this should correspond with the decimal that we got for x when we looked at the graph. And indeed, I do get negative 0.18, which is exactly what we saw on the graph. All right, so those are some examples there. Okay, so all the examples we just did had one solution. And what that means graphically, we talked about that's where they cross. That's where the lines cross. So we can see in this picture, the solution is the exact point where the lines cross. Sometimes when I ask for a solution, I'll just ask for x. Sometimes I want the ordered pair, so like the x comma y point. But that's what that means graphically. Algebraically, what it means is when we isolate the variable, we get an actual number. So like for all of these examples, we got x equals negative 0.18. We got x equals negative 0.75. We got x equals negative 1.5. So we get x equals a number. Now, there are two other scenarios that we can have. So we just talked about the first scenario. So there's three scenarios in total. The first scenario we just talked about was one solution, so that could happen. However, it could be that the lines never cross each other. And in that case, what we have is no solution. So graphically, the lines are parallel. They never cross each other. And what does this mean algebraically is that when we try to solve the equation, we end up with an untrue equation at the end. And what that means is that, as we talked about in a few videos ago, we're going to get two different numbers equaling each other. That means an untrue equation. That's what we call like a logical fallacy, a mathematical untruth. We get 2 equals 3, negative 4 equals 6, 0 equals 18. Things like that are untrue. And we're going to do some examples where we can actually see this in action. So these are the first two cases. And the third case is that we could have infinitely many solutions. And what that means is we're going to have two lines that are given, but they're going to be disguised to look different. But they're secretly the same line. You see, x plus 2y equals 3 and 2x plus 4y equals 6 are actually the same line. Like, if I rearrange this first one, I have x plus 2y equals 3. If I try to isolate y, I'm going to first subtract x on both sides. And then I'm going to divide both sides by 2 to get y alone. And when I do that, I get y equals 3 over 2 minus 1/2 x. Right? That's my first line. And if I do the same process for the second line, if I solve for y with the second line, I get the following. Draw my equal sign. I'm going to subtract 2x on both sides to isolate that y term. And then I'm going to divide everybody by 4 to isolate y. And so on the left, I get y equals, well, guys, 6 divided by 4 can be reduced by 2. If I divide the top and bottom by 2 to reduce it, I get 3 over 2. And if I reduce 2 over 4 right here, I get 1 over 2. So these are secretly the same lines, okay? So that's what infinitely many solutions mean, is if at the end of the day we get the same line. And what that means in Desmos is that when you plug in these two things in Desmos, you're going to get just one line. You're not going to get any kind of intersection. What this means algebraically is that you're going to get a true equation. So, for example, 1 equals 1, negative 5 equals negative 5. A number equaling itself is a true equation, and we're going to do some examples where we actually see this in action. Okay, so here's the steps to find solutions graphically. We're going to make sure that the left and the right side of the equal sign are in y equals mx plus b form, and then we're simply going to plug these two things into Desmos and look for the point of intersection. So for example, we have two lines. We have this line, and I know that these are lines, even though they're not in y equals mx plus b form. I know that they're lines because the variable x doesn't have an exponent, okay? So like, if there was an x squared on there, or like an x to the third, I know that's not going to make a line shape. However, since there's only x's, it doesn't matter how many x's I have. I could have, because they're still like terms. So what I'm going to do is I'm going to simplify both sides independently of each other without moving anything across the equal sign. And to do that on the left side, I'm going to use a distributive property first. Negative 2 times x is negative 2x. Negative 2 times 4 is negative 8, and I still have that negative 1 at the end. When I do it on the right side, I can distribute the 6 in there, and 6 times x is 6x. 6 times negative 1 is negative 6. So on the right side, I'm good. I have mx plus b. M is 6 and b is negative 6. On the left side, I can combine this negative 8 and negative 1 because they're like terms to give me negative 2x, and then that combined is negative 9 equals 6x minus 6. So at this point, we can use Desmos because we're in mx plus b form on both sides. On the left side, m is negative 2 and b is negative 9. On the right side, m is 6 and b is negative 6. So let's put this in Desmos. Okay, I just want to make sure I had the right lines. So I'm going to zoom out, and then I'm going to look at their intersection, and they do indeed intersect at negative 0.375. So that is their solution. And again, sometimes I'll just ask for x as the solution. Sometimes I'll ask for the ordered pair. So like negative 0.375 comma negative 8.25 would be an acceptable answer as well. So that's how you do that with the graph. Now, if you want to do it algebraically, you just solve the equation, just like we've always done. So remember, there's 3 different situations you could get. You could get one solution where we get a variable equals a number. We could get a false equation. In that case, we would have no solution. And if we get a true equation, such as 2 equals 2, 3 equals 3, we have infinitely many solutions. So those are our three options. Now, in this option, we had one solution, right? So this is the same equation as before. So let's prove this algebraically that we do get exactly one solution. So what I'm going to do is I'm going to start by distributing this on the left and the right. Negative 2 times x is negative 2x. Negative 2 times 4 is negative 8. We still have the negative 1. On the right, when we distribute the 6, we get 6x minus 6. Now on the left, before I start moving things, I'm going to combine these terms to negative 9. And at this point, I want to isolate x. So I'm going to start by undoing subtraction of 2x by adding 2x to both sides. And when I do that, on the left side, I'm left with negative 9. On the right side, I'm left with 8x minus 6. 6x plus 2x. Now I can undo subtraction of 6 by adding 6 to both sides, and that's going to give me negative 3 equals 8x. Finally, I'll divide both sides by 8 to give me x equals negative 3 over 8. And in the calculator, I get negative 0.375, which is what I got before on the graph. So that's how I can verify this algebraically. This is exactly one solution. So that's our first scenario. So let's do some other problems here. How many solutions does 2x minus 1 equals 8x minus 7 have? So since these are in y equals mx plus b, we can look at this graphically and algebraically. So again, this is our m2, our b is negative 1, m is 8 on the other side, b is negative 7. I'm going to go ahead and solve this algebraically and look at it graphically as well. So we have the algebraic equation 2x minus 1 equals 8x minus 7. I'm going to first start by grouping my x's on one side by subtracting 2x from both sides. And when I do that, on the left I get negative 1. on the right, I get 6x minus 7. And then I'll go ahead and undo subtraction of 7 by adding 7 to both sides. And when I do that, on the left side, I get positive 6. On the right side, I get 6x. And then I'll finish off by dividing both sides by 6. So x is equal to 1. That's one solution. I got x equals a number. So my answer here is 2. I can also look at this graphically by putting both of these lines into Desmos, right? 2x minus 1 and 8x minus 7. And then seeing where their point of intersection is. And we can see that they do indeed intersect at x equals 1, so that is their solution. Let's do another example. We have negative 5x plus 7 equals negative 5x minus 3. So graphically we're good to go because we're in mx plus b form on both sides of the equal sign. On the left side, m is equal to negative 5 and b is equal to 7. On the right side, m is equal to negative 5 and b is equal to negative 3. So let's look at this algebraically first and then confirm our solution graphically. So we get negative 5x plus 7 equals negative 5x minus 3. What I'm going to do first is I'm going to get the x's together by first adding 5x to both sides. And they actually end up canceling out on both sides. So I'm left with 7 on the left side equals negative 3 on the right side. This is a false equation, an untrue equation. And so that means, sorry, that was my cat. That means that there are no solutions here. All right. Let me let her out. Okay. Quick intermission there. Now let's prove this to ourselves graphically. So let's put this in Desmos, these two lines. Negative 5x plus 7 and negative 5x minus 3. Oops. Okay. Now if we zoom out, we can see that these things are never going to intersect. So these are parallel lines, which means they don't cross. And that tells us that there is no solution. 0 solutions. So this is a cheat code that I'm going to give you guys. So if the lines have the same slope, the same steepness, and different y-intercepts, we have no solution, 0 solutions. So that's our cheat code here. We can see that both lines have negative 5 for m, and the y-intercepts are different. So no solution there. Let's do another example here. So let's go ahead and solve this algebraically. So we have negative 3x minus 5 plus 1 equals negative 3x plus 16. So first thing I'm going to do is I'm going to get rid of the parentheses by using the distributive property on the left side. So negative 3 times x is a negative 3x. Negative 3 times 5 is a positive 15, and I still have that plus 1 tacked at the end. So on the left side, I can combine the 15 and the 1 to make 16. And so I get negative 3x plus 16. So hopefully you guys can see where this is going. We have the same exact line. So remember what that means graphically. If you put this in Desmos, since we're in mx plus b form on both sides, we're going to get the same exact line, right? There's no difference between the two. Now, what does this look like algebraically? Well, algebraically, if I add 3x to both sides, those are both going to cancel out. And what I'm left with on the left side is 16, and on the right side, I'm also left with 16, which is a true equation. And that tells me algebraically that there's infinitely many solutions. Now again, graphically, I'll let you guys verify this. If you put both of these lines in, you're going to get just a single line. And that's how we can verify that graphically. Okay, so let's do this one. Solve the equations algebraically and graphically. So I'm going to draw my line through the equal sign, and I'm going to use the distributive property on the right side first to get rid of the parentheses. So on the left side, nothing really changes here. On the right side, 5 times x is 5x. 5 times positive 1 is positive 5 using the distributive property. And then I have that plus 1 at the end. So on the right side, I can combine like terms before I start moving things. 1 and 5 make 6, so this is 5x plus 6. And now I can subtract 5x from both sides, which cancels out on both sides, and I'm left with 4 equals 6. This is an untrue equation, so this tells me algebraically that there is no solution here. They are never going to cross. Now, graphically, I can use my lines from this step, because both of these are in mx plus b form. I'll write it over here. 5x plus 4 equals 5x plus 6. So this is m, this is b, this is m, this is b. We know from our cheat code, since we have the same slope and different y-intercepts, that they're not going to cross. But we can put this in Desmos as well. Okay, and we can see that these guys are parallel. They're not going to cross anywhere. So, no solution. Okay, let's do this one. So, let's go ahead and first look at this graphically, and then we'll solve it algebraically. So, the left side is okay because it is technically a line, like y equals 3 is a line. We don't have, we have 0 for the slope. So we can actually write this in y equals mx plus b by writing 0x plus 3. It's the same exact thing as just 3. So m is 0 and b is 3. On the right side, we can separate the fractions out since the two terms on top are all over a single number. We can separate them out as 2/3 x plus 1/3. And at this point, we're also in mx plus b form. So again, on the left side, m is 0, b is 3. On the right side, m is 2/3, b is 1/3. So let's go ahead and look at this in Desmos. So 0x plus 3. And then the second one was, 2/3 x plus 1/3. Okay, so now we can just see where their intersection is, and it looks like they intersect at x equals 4. So that's where they cross each other. So that's how we know our solution's x equals 4. So exactly one solution. And that solution is, not 3, 4. Now let's do this algebraically. So on the left side, the 0x is just 0. So we have 3 equals 2/3 x plus 1/3. And on the right side, I can clear the fractions by multiplying by 3, multiplying both sides by 3. Right? And so on the left side, 3 times 3 is 9. On the right side, 2/3 times 3 over 1 is just 2, right? The 3's cancel. And 1/3 times 3 over 1 is just 1. The 3's cancel. Oh, I'm sorry, 2x, not just 2. So on the right side, we have 2x plus 1. On the left side, we have 9. Now I can solve for x by first subtracting 1 from both sides to give me 8 equals 2x. Now I'm going to divide both sides by 2 to give me x equals 4, and that is exactly what I got up here. So there's exactly one solution, x equals 4. Let's go ahead and do this one. So The left side looks good. We're in mx plus b form. The right side we need to clean up a little bit. So to clean it up, I'm going to use a distributive property as usual, and 9 times x is going to give me 9x. 9 times -1 is -9. On the other side, I'm left with 9x plus 4. And so I can combine these terms here to give me 9x plus 4. So I think you guys can see where this is going here. So these are my two lines. When we put them in Desmos, we're just going to get one line because they're the same line. 9x plus 4, 9x plus 4. So that one line is going to tell us there's infinitely many solutions. What that means, guys, is that in any step of the equation, step 1, step 2, step 3, any of these lines, I can plug in any number I want for x and get a true equation. So for example, with the first line right here, if I plug in x equals 100 on both sides, I'm going to get a true equation. If I plug in x equals 86 on both sides, I'm going to get a true equation. So that any x you can think of is going to give you a true equation. That's what that means. So we know that our answer is infinitely many solutions. We saw that graphically. Now to continue this process here, if I solve for x, I'm going to subtract 9x on both sides, and I'm going to end up with a true equation, 4 equals 4. So that's how I prove to myself algebraically that there are infinitely many solutions. Okay, let's go ahead and look at this one. So this time our variable is t instead of x, which is okay. If I look at the left side, I can clean it up a bit. So what I can do is I can first distribute that 2 in there to make it look a little bit more familiar. So 2 times t is going to be 2t, and 2 times -5 is -10. That's all over 3. And this, on the left side, this is again one of those cases where the slope is 0. So this is just 8 plus 0t for x. What I can do at this point is, let's see, I really don't want that fraction there. So what I can do is I can actually multiply both sides by 3 to get rid of it. I gotta multiply that guy by 3 and that guy, and when I multiply 3 by this guy, the denominator is gonna go away. So 3 by the first guy, 3 times 6t is 18t. 3 by the second guy, again, is gonna clear the denominator to just leave me with 2t minus 10. On the right side, 8 times 3 is 24. And so on the left, when I combine 18 and 2, I'm gonna get 20t minus 10 equals 24. So on both sides, I'm in y equals mx plus b form. Since t is acting like our x, 20 is m, and -10 is b. And over here, 24 is b, and m is 0. So I can put this in Desmos. Now remember, Desmos likes x's. It doesn't like other variables. So I'm going to put 20x minus 10 in for 1. And then for the other one, I'm going to put 24 plus 0x. All right, so we can see that they cross right here. And so x is going to be 1.7. Or t, rather. So we can see from the graph that we have exactly one solution. Remember, our choices are exactly one solution, no solutions, or infinitely many solutions. Okay, now if I continue to solve this for t, I'm going to first add 10 to both sides. And I get 20 times t is equal to 34. divide both sides by 20 to get 34 over 20, which should equal 1.7. So that's how we can finish the job off algebraically. Okay, so we want to solve the equations algebraically and graphically given h of x is 4 and h of x is 2x over 5x minus 1. So when we first started looking at function notation, we said that, f of x, g of x, h of x, all of these things basically mean y. So if it makes it easier for you, you can go ahead and replace h of x with y. Now, since y equals one thing, which is 4, and y equals another thing, 2x over 5x minus 1, we can set those two things equal to each other because they both equal y. Alright. And if we look at our equation, the right side isn't quite linear yet. It's a rational function, meaning we have a variable in the denominator. But what we can do is we can actually go ahead and multiply both sides by the denominator on the right side, just like we did in previous problems. If we had a denominator of 3, to clear the denominator, we would multiply both sides by 3. Well, here, to clear the denominator on the right side, I'm just going to multiply both sides by 5x minus 1. And on the right side, those are going to clear, right? That was the point of that. And I'm just left with 2x. Now, on the left side, I need to distribute the 4 in there to the 5x minus 1. So 4 times 5x is 20x. 4 times minus 1 is minus 4. And from here, I can group my x's on one side by first subtracting 20x on both sides. So on the left side, I get negative 4. And on the right side, I get negative 18x. And finally, what I can do is I can divide both sides by negative 18. And when I put this in the calculator, let's see, negative 4 divided by negative 18, I'm going to get 0.222. And if we look at this step right here, we are in y equals mx plus b form on the left and the right hand side. On the left side, m is 20 and b is negative 4. On the right, m is 2 and b is 0. And so when I zoom out of here, I click their point of intersection, and I do see that they intersect at x equals 0.22, just like we verified algebraically.